In calculus 1, we connected the antiderivative to the area under a curve using the fundamental theorem of calculus. Now we have an antiderivative. Well, it's not quite an antiderivative in the normal sense. But how do we connect it to the area under a contour, so to speak? I hate this chalk. Well, that's what the subject of today's video is. How do we prove the fundamental theorem of calculus for complex numbers? Well, to start, let's just reprove. Right, this is dead. Where'd I leave the marker?
It's quick to take a marker from their basket. It's a double-sided marker.
There's a brown one.
Yeah, brown one. Take the brown one. Or black. Give it to me.
Okay. Here we go.
Oh, here's the black. Black, not black, no.
Okay. So, how did we prove the fundamental theorem of calculus? Well, the fundamental theorem of calculus' statement is this. The integral of f of t dt from a to b is equivalent to f of b minus f of a. If f is the primitive i.e. antiderivative, and you can kind of get where the name comes from because derivative is something that comes after an original thing that has some features changed. And so, of course, the opposite of a derivative is going to be the primitive version, the first. So, this is what the fundamental theorem of calculus tells us. So, how do we extend that to complex numbers? Well, we have to start with the fundamental theorem of calculus, just write FTC, for complex Riemann integrals. What is a Riemann integral in complex numbers? Well, there's nothing stopping you from taking a complex function and integrating it over a contour that's only all on the real numbers. But of course, a continuous contour over the real numbers is going to be equivalent exactly to just a real interval. So it's what would happen if you try to take the real integral of a complex function. So what happens when we try to do that? Well, for this, we have to bring out our good old Cauchy-Riemann equation. So let's do this. We start by taking the integral from a to b of f of, let's call it t dt. And now we take this and realize it's exactly equal to f of t, let's call it z, plus 0i, where t is some real number, since of course z has no imaginary component. So then, that's where you bring in the Cauchy-Riemann equations, where you get, this is the integral from a to b of partial t u, where u is the real part of f, t0, plus I partial t v t0 dt. And now we can split this up. Notice how the real part of this function is, a real number. The imaginary part of the function is also a real number. Remember, m of a plus bi is b, not bi, which means the imaginary part is also real. This is real, this is real, so we should be able, and we're integrating over a real contour, we should be able to just apply the regular FTC. So this should become u of b0 minus u of a0 plus I times v of b0 minus v of a0. But wait a second, f is just u plus iv. So this is equal to u b0 plus iv b0 minus u. Where did I put the other cap? That's interesting. Minus u a0 minus iv a0. So, at the end of the day, this is just f of b minus f of a. There we go. That's the FTC for Riemann integrals. So what about in general? What about a contour that is not just on the real numbers? Well, we first bring out the definition of a complex contour. So this is f over gamma, and that's equal to, from t equals a to t equals b, f of t, gamma prime of t, dt. Now what do we do? Oh, hey, wait a second. T is a real parameter. It's always going to be real. Of course, gamma itself is complex, but that doesn't matter because this part is real, and so is this. Hey, wait a moment. Why can't we just we take this as equal to, by the chain rule, d dt f of gamma of t, where f is the primitive of little f. And so this is a real, this is complex, but the t inside it is a totally real parameter, which permits us to use the theorem for complex Riemann integrals, since even though the result is going to be complex, whatever's inside the parameter we're integrating over is real, which means this is just going to be f of gamma of b minus f of gamma of a. And that also means for a closed contour, the integral is going to be 0. Oh my goodness. But wait a minute. I said last time that there were some integrals that were path dependent. That is, they're not just dependent on the endpoints, they're also dependent on the path you take to get there. But, I mean, where's the hole in this proof for every single function? Wait a second. We cited the Cauchy-Riemann theorem, but that only works for holomorphic functions, or analytic functions, functions that are infinitely differentiable, or once differentiable. So if a function is not complex differentiable anywhere, this theorem no longer makes sense, unfortunately. But aside from that, this works for every single complex differentiable function. On any closed contour where both of the endpoints are the same, the contour integral is going to be 0. That is a very important fact. So that's it.